Hi, welcome to part 4 of our Python course. This part is completely optional and thus offered to you as an offline recording. Feel free to watch it at your own pace. The topics presented here are a bit advanced and may require a bit more time to absorb. They, however, emphasize important relationships between a few core programming concepts, and their understanding may help you in mastering the rest of the material faster and in becoming more seasoned coders later down the road. The first thing that we want to explore is the fact that functions are standalone objects. All the binary operations that we are so used to are in fact performed by calling functions that are members of the number objects. Whenever we write expressions like 3 plus 4, what Python does in the background is convert this expression into an expression of this form, right? So we're saying 3 dot add applied to 4. So we're going to learn later what objects are, but just as an intuition, 3 as a number, it is also an object, and every object in Python comes with all the operations that the object can perform. So for instance, the object 3 has an operation called add that makes it possible to add numbers to the number 3. So therefore, as we write 3.add, this is a function that adds 3 to its argument. All right, and we're going to see this notation a lot. We see the dot here, and the dot separates the object from its feature, right? If we want to access features from inside the object, addition is a feature of the number 3. So we're saying 3.add to select the function that adds 3 to its argument. An alternative notation is the one that is coming from class int. So the object 3 is an instance of class int, and therefore the class int would have a feature to add two numbers together. And this is what you see here. Right, class int dot add is a function which can be applied to arguments 3 and 4 to produce a result. And we have seen this in one of the previous lectures. For instance, we can write things like f is defined as 3 dot add, all right, and then we can apply f to 4 and we get a result. So from this point on, f is the function that adds 3 to its argument. Alternatively, we can say a equals int dot add, right, and from this point on, a is a function that adds two numbers. All right, this becomes a much simpler and much more straightforward notation that can replace lambda x, for instance, x plus 3. Right, so we know that this is a function, and we can use this function to apply it to anything such as 4, right? And we always thought of this notation as being slightly more cumbersome. From this point on, we have this as a much more direct notation. You would expect that addition should be a built-in function, right? And it so is. All right, so let's see how we can take advantage of functions as entities. The first thing that we're going to learn is mapping a function over an iterable, and we have learned that all collections are essentially iterable. What an iterable allows us is to go through the elements of a collection in a predefined order, which we don't necessarily care about, and make sure that every element in the collection is considered, not leave any element out, right? And one interesting thing that we can do is to apply a function to every element in an iterable. So assume that we have this list of integers, right? And we want to apply this function to each element of that collection, of that list, and produce a collection of the results of the applications, right? So I take the selected list and first apply it to 10, and then apply it to 20, and then apply it to 30, and then apply it to 40, and I want to obtain 13 followed by 23 followed by 33 followed by 43, right? So this is in principle a interesting application. It's very useful. This map is predefined in Python and readily available. You don't have to import any module to do that, right? And we can see how this works by simply typing it into Python. All right, and it performs what we expect. You might wonder, why do I need to say list here? Because map returns a iterable, right? And an iterable, so let's repeat this expression without the list. An iterable is something that, when evaluated, doesn't say what it has inside, right? So in order to force this object to reveal its contents, we have to convert it either into a list, or let's say a tuple, all right, or a set. So we can very similarly use a set here, right, and so on. And notice that when I use a set, the order has changed. So mapping can be very versatile. For instance, we can do things like, and again, I'm going to use list in front just because we want to see the contents of the result. Map applied to, and let's produce a list that of a function that squares x times x, and lambda, and say a list of the numbers 4, 2, 6, 3, 9, and we close the brackets, and what we get is a list of the squares. So anytime we want to apply a function multiple times to multiple arguments, we can just produce the function here and use the map to perform that operation. The next operation that we want to learn, the next higher order operation, is called filter. It allows us to select a subset of a collection, right? The elements that satisfy a given predicate. So the format is filter. We have the predicate, and you might guess that this predicate that we have here as an example is all the numbers that are greater than 10, right? All the numbers of which 10 is less than or equal to. All right, and we're going to look at this list, and we're going to select, of course, those that are greater than 10. So let's take this expression and evaluate it in Python. All right, and you can see that this is happening, right? Obviously, as you might expect, 10 as an integer would have, among other operations, the one that can compare against the ones that can compare against other numbers, right? Less than, equal, greater than, equal, equal, and not equal, right? So all those will be in there. One way to find out all the operations of 10 would be to execute or invoke dir of 10, right? Which it's pretty much the same for all the integers. And you can see here that we have an operation for greater than. So let's start with them in order. So there's one for equality. For some reason the cursor doesn't work quite well in the Mac OS Python, Mac OS idle. There's greater equal, there's greater than, so greater but not equal. There is less equal. Unfortunately, it's printed on 2 rows, right? So less than equal. There's less than. And there's not equal, right? All of them appear here. As alongside all the arithmetic operations. So here, since we're right here, you can see the multiplication, and if you look carefully, there is subtraction, there is division, there is modulo, and so on. Right? So any operation that has a Boolean result can be employed here. All right, you can make up your own, and you can make complicated expressions. So let's say we want to select the numbers that are between, let's say, 7 and 10. All right, so how would we do that in using filter? So again, I'm going to use list because that's what tells us what the content of the result is going to be. Filter, and I am going to have lambda x, and I want x to be smaller than or greater equal to 7, and x to be smaller equal to 10. All right, and then here we can copy this list, and you get all the numbers that are between 7 and 10. Right, so the important aspect for filter is that this expression right here is a Boolean expression. It returns either true or false. The next part is performing zipping operations. This operation, the zip, doesn't employ functions per se, but it's an operation that is very useful in using functions, because we will often want to employ functions of multiple arguments, and then we have to somehow aggregate the arguments together. We have a list of elements that we want to be the first argument, we want another list of elements that we want to be the second argument, and in order to be able to create separate invocations for each instance of first and second argument, we have to put them together in either a list of pairs, a list of tuples, right, list of pairs, or a set of pairs, or whatever, right? If we have functions of 3 arguments, then we will need triples. We will have 3 lists, and we need to assemble them into triples. So this is another function that is built in. You don't need to load any module for this, right? And by now I think you can believe that whatever I evaluate actually reevaluates to the result here. So in the spirit of making things a little bit, the pace a little bit faster, I'm just going to skip the evaluation, right? So what zip does is, right, it takes multiple collections, right? All these collections must have the same size, otherwise the longer collections will be truncated to the size of the shorter collections. All right, and it will produce a collection of tuples, right? In this example, we have two lists, so then we get a list of pairs. You see that the first argument here is paired with the first argument here, right? Then if you look at the second argument of the result, the second element in the result, you see that the second argument, the second element of the first list is paired with the second element of the second list. Then further, the third element of the first list with the third element of the second list, and so on and so forth, right? So what we get in the end is a list of pairs. And if we have a function of two arguments, we're going to see that we can map on this list. So that's going to be the objective of using zip. We can map of this list, and we can pass two arguments to that function. We can make each pair into essentially two arguments going into the function. Let's look at another example where we take zip and we apply it to three separate lists. All right, and then we're going to produce a list of triples. This is the first triple, which has the first elements of each of the three arguments. This is the second triple, the third, and the fourth. Okay, so now we have learned in a previous lecture that we can convert tuples into separate arguments by using the star notation, which is what we use here. Okay, so we're going to define this as a function. We're going to create a function that converts another function from its multiple argument version to its tuple version. All right, so I am going to play with this a little bit just to give you a bit more insight about how it works. All right, so we define this function. All right, and let me tell you first what we are talking about. So remember that the function add, int.add, takes two arguments. Right, let's remember that first to understand what's coming next. Right, so int.add, all right, and instead of that, I can pass in a tuple. All right, and it doesn't look like magic, but let's look at something. Let's look at it a bit differently, right? So let's say I create a tuple which has the value 3 and 4, and then I can say int.add, apply to star t, and I get the result. Even though this function by nature takes two arguments. Right, this is a function of two arguments, but we have converted it into a function of a single argument, where that argument is a tuple containing the two arguments. All right, now the star function performs that conversion. All right, so let's say I say f is assigned to star of int, sorry, okay, so let's say we say this, right? So now what I can do with f is I can apply it to a tuple. I can apply f, apply it to t, I'm going to get 7, right? So this f has become the tuple version of this function of two arguments. All right, so this is a very powerful transformation. Star is a very powerful function. All right, so let's see how this can be of use to us. All right, so let's go to what I was telling you previously. All right, we have two sets of arguments. This is a list of elements that we intend to be the first argument to my function, and this is the list of elements that I intend to be the second argument to that function. This zip is going to create the tuples. Tuple the first ones, tuple the second ones, tuple the third ones, tuple the fourth ones, right? And then I want to add them together. So I want add 1 to be added to 10, 2 to be added to 20, right? So because my list is a list of tuples, I cannot directly apply this function which takes 2 arguments. All right? If I map that function directly on this, then each invocation of add will take a single argument, which is a tuple. Will not take 2 arguments, but a single argument, which is a tuple, right? This is a type mismatch. We have to fix the type mismatch by wrapping the function with star. Star int add is no longer a function of 2 arguments, but it is a function of a single argument, which argument is expected to be a tuple. So at that point, this expression will evaluate to this result, all right, where each of the 4 pairs of numbers have been added together, right? 1 and 10 is 11, 2 and 20 is 22, and so on and so forth. Now, this map applied to star is actually a predefined, a built-in function, right? It resides in the module called itertools, all right, and has the name star map. So star is not very frequently needed, because whenever we need to perform this trick, we will have functions that already are capable of taking tupled, converting functions of multiple arguments into tupled functions internally, right? So our expression becomes this. There's no need for star, but nevertheless we use not map anymore, but star map. Okay, so I think this is a very neat trick. Now, what if we want a more sophisticated function, one that, for instance, is capable of working on triples? All right, for instance, sum can take in triples. Let's remember that. Let's see that if I apply sum to a triple, right, we get 6. So sum takes a collection. If I say 1, 2, 3, this will result in an error. Sum cannot take multiple arguments. It has to take one argument, which needs to be a collection. It will work with a list. Oops. It will work with a list. All right, but it will also work with a tuple. Tuple is also a collection. It will not work without a double set of brackets. So coming back here, now since sum takes tuples, we can use map and apply it to the zip of 3 lists, and we will obtain the list of results. Next week we're going to talk about curried versus uncurried functions. So in order to explain what curry stands for, well, it comes from the name of this guy. All right, who has 3 languages. Each of his names actually led to a language, and he invented the concept of currying, about which you can find more here. All right, and currying leads to the ability to apply functions partially. All right, and that leads to a very elegant functional algebra, which many of the programming languages that we know have missed on, right? There are a few, most importantly Haskell and OCaml, that take full advantage of that, but not Python, all right? But we're going to try to simulate that in Python and create a similar kind of concept and show that somehow that is still quite useful, that still can be very, very useful. So Python is not a curried language, right? And we will say that it's an uncurried language, and all the functions that we create in Python are uncurried. So the typical version of a plus function would be something like this, right? Uncurried plus would be something like this, right? Which is precisely equivalent to int.add, I might also say, right? But the important thing is that in order to invoke this function, we use two arguments in the same set of brackets, right? Two arguments in the same set of brackets, right? Now I am going to come up with a different kind of definition, which we could say curried, right? Notice that instead of separating the two arguments by a comma, here we put the two arguments in separate lambdas. So I'm going to say it's lambda x applied to, or defining lambda y, and finally getting x plus y. All right, and this is what we say the standard functional way. It comes from functional programming. Now if I want to invoke this function, I have to invoke it this way. Okay, why? Well, curried plus applied to 3, right? This 3 becomes the x, and the value of that is another lambda. So that lambda can be further applied to 4 to yield the result. So notice the difference in syntax, right? I have to apply to the first argument and then separately to the second argument. The arguments are not within the same set of brackets. All right? So now, whenever we have a function like this, right, we can apply it partially. So because of that, applied to 3 is equivalent to add, right? So here we are lucky to have a predefined version of addition, right? But for other operations we won't have that, and working in a curried way allows us to partially apply a function. We instantiate some of the arguments but not all of them. Okay, so that's an important distinction. Now the transformation between curried and uncurried is very simple, right? We can define very simple functions that performs the currying and uncurrying for us, right? So this is it. I take a curried function of, presumably this is a function of 2 arguments, right? And then I'm going to return lambda x, lambda y, uncurried f applied to x and y. Okay? And I can perform the reverse. I can take a function, curried function, presumably of 2 arguments, and I can return lambda xy, and then I apply curried f first to x and then to y. Okay? So you see, if I take curry applied to uncurried plus, then this highlighted expression is a curried function. I have to apply it first to 1 and then to 2. All right? If I apply uncurry to curried plus, so if I take this highlighted expression, right, this has become a Pythonic way, a Pythonic function again, right? So it has to be applied to 1 and 2 simultaneously, right? But we know that curried plus, the one that we see here, the one that we have defined here, actually needs to take the arguments separately, right? But by the simple application of uncurry, we have made it back into an uncurried function, right? So now, curry applied to uncurry boils down to the identity. So that's a very interesting thing, right? So if I apply curry to uncurry to a function, I get back the same function, right? And if I do the mirror of that, uncurry applied to curry, again I get back the identity function. I get the same function back, right? Whatever argument I put here, the result, which is this expression, this expression, right, is the same as whatever function I put within the innermost brackets. So these are interesting properties, right? They can be mathematically proven, as a matter of fact. Now, guess what? We do have a predefined curry function, right? We don't have to define it ourselves. And it is a particularly interesting function, right? So you have to install this module using pip. So you're going to have to say pip install pymonad, right? And then you're going to have this operation available. And this operation is available as an annotation. And here is what a new concept being introduced in Python, that of annotations, right? And if we annotate this function with this annotation, then this function becomes available in both curried and uncurried versions, right? So let me repeat that. From this point on, this uncurried plus, actually it is also curried, all right? So I can apply it like this, all right? I can apply it like this. Both work. There's no problem. I can apply it like this, all right? And that works too, okay? So this is a very cool feature. And then we can partially apply it, right? I can apply it only to one. So this becomes similar to one dot add, right? So even though I have defined here a function of 2 arguments, I can apply it to only one, and I get the function that adds 1 to its argument. And then later I can apply add 1 to some argument, say 2, and that evaluates to 3. Okay? And guess what? I can do this for as many arguments as I want. So let's say I define an uncurried plus of 3 arguments, right? X plus Y plus Z, all the 3 arguments added together. And now I have a lot more options, right? So from the definition, you would know that this is possible, right? But this curry annotation would make it possible to apply it in this way and in this way. Sorry, the highlighting in idle is really, really bad. And then in this way. Okay, and it can also be applied partially. So this is the function that adds 1 to its second and third argument, right? And then so we get h1. Now I can apply h1 to one more argument. I get h2, and h2 applied to 3, and only then we get an integer value, right? So h1 is a function, h2 is another function, right? So h1 is the partial application of uncurried plus, h2 is the partial application of h1, and h2 applied to 3 yields the result 6. This is a really cool feature, and we're gonna see some applications of it soon. All right, so the next element that we introduce is functional composition. We have introduced currying, and we have seen a particularly useful kind of currying utility. And then we want to introduce functional composition and show that with these two we can do quite a lot of stuff. So let's try to understand what functional composition means by using an example. So let's say we have two procedures or functions in this case, because they don't have side effects. So we have one that is called distance and computes the distance between origin and the point of coordinates x and y, right? Which would be the square root of x squared plus y squared. And the other one which scales a value by 2, right? And it simply multiplies that by 2. So if I want the double of the distance of a point, right, we could perform an operation something like this, right? We scale by 2, the distance 3 to 4, and this evaluates to 10. Now, we may want to do this for many sets of arguments, right? So we could define our own function, right, that takes scale by 2 and applies it to distance of x and y, right? And we can now use this function for any pairs x and y we need. But the question is, can we define this in a more quirky way, right? So depending on the language we use, it might appear that it is easier or more difficult to define it in a different way, and it will kind of appear more complicated in Python, but still doing it without using defs and lambdas, because this is the purpose, to do it without defs and lambdas, is still a very interesting exercise, even though we are doing it in Python, right? So for the remainder of this section or of this segment of the lecture, we are trying to find a new way of defining functions that don't require defs or lambdas. But they will rely on some other primitives, such as currying, and as you will see right immediately, right, that the other primitive is compose, functional composition. Functional composition is something that you should know very well from mathematics, right? So we used to do things like f applied to g applied to x, and this can be rewritten as f composition, and I'm going to write O for a circle, G applied to X. Hopefully you remember that, right? So this O, which appears as a infix operator here, is not available as an infix operator in Python, so we have to use it as a function. So essentially we're going to write the O applied to F and G and then apply to x, right? And this O of f and g as a standalone expression is the composition of a and g. And guess what? O is not the actual identifier that we use here, but the identifier is called compose. So you're seeing here that from functional, this is yet another module, we import compose. Compose is a function that composes to other functions, right? So we can take compose and apply it to the function that adds 3 to its argument, and the function that multiplies 4 with its argument, right? So we can do that. And what do we get here? Notice that this is a standalone expression, and that expression is further applied to 10, right? So this highlighted expression should have a result of its own. Right? And what is that result? Well, it's the function that applies, so this highlighted function, right, must have a result of its own. And it's the function that multiplies 4 to its argument and then adds 3 to the result. Right? Multiplies by 4 and then adds 3. So this is what it is, right? I can take this and call it f, right? And then I could apply f to 10 and get 43. So this is the function that multiplies by 4 and then adds 3. Notice the use of the composition. Okay? Now, what if we didn't have this compose? Well, we could easily create our own, right? And this is always a very useful exercise. If you didn't have it, how difficult would it be to create your own, right? And sometimes it's very difficult, like with the sine function, you would not be able to easily produce a very precise approximation of the sine function by yourself. Not in it will probably require a lot of expertise, you learning a lot about the math behind the approximation, and then writing code for a few weeks. So you will probably need a few months to get the job done, right? So it will not be an easy task, but it's always useful to ask the question, because you will kind of understand how much complexity is there in your code. So if compose didn't exist, then we could write our own version, right, which would look like this, right? It takes f and g and it returns lambda x, f applied to g applied to x, and that's it, right? So luckily compose does exist, and we don't need this my compose. Now we're going to do a trick. We're going to replace the stock, the built-in compose, by a curried version. So that's going to be even more interesting. We're going to replace it by a curried version of compose. And notice how we do this, right? We reuse the name, so we delete the old name, right? We don't delete the old function, because this curry still refers to this compose. This is the old compose, right? So first this expression gets evaluated, and then the result gets assigned here. So since the old version of the function is still referred to by curry, it doesn't get garbage collected, right? And this compose is a new is the same name used to a new function that takes curry, currifies the old compose. So now if we do this trick, we can write the scale distance. Remember the scale distance that we were talking about here. We can write the scale distance in this way. Now this is a longer expression, right? But it would be interesting for you to take a good look at it and figure out why it works. All right? It's like a puzzle. And this sort of gives you a glimpse at the fact that if you consider compose and curry as primitives, as given by the language, right? Which in Python they're not, but there are other languages that do have this as primitives. So if you do this, you do not need def and lambda. You could define any function in this way, right, as an expression using compose and curry. All right, so this is performing precisely the same computation as this, okay, and it will evaluate to 10. Up to you to figure out how this works. Now we're going to employ a little trick, and this is because Python is built the way it is built. All right, so we're going to have a wrapped curry. Notice that this wrapped curry doesn't do anything. All right, it returns the same result as curry, but if f is a built-in function in Python, then f is implemented in C. All right, and because of that, because of a technical flaw in the way this curry is implemented, curry cannot apply to f directly, to f built in, because f is built in directly in C, right? So if I were to write f, and f were a built-in function like int dot add, right? This will bump. This will result in an error, which will be a very arcane error, very hard to comprehend, simply because this is implemented in C. So we put a wrapper around any function, right? And this wrapper is this lambda. Notice, if you look very carefully, that this lambda doesn't do anything. It takes arguments and passes them inside f. So it will never return any other result than f. For all intents and purposes, this works precisely as f. This expression and f are indistinguishable. All right? But because at the compilation level, there's a wrapper on f, then Cari can work properly. So we're going to need to use wrapped Cari every once in a while. All right. So the homework that you have here actually should apply to this. Figure out why this works. Figure out why this works. The thing we look at is partial application. All right, and we already know how to perform partial application, but we want to use a predefined a built-in function for that, right? So far we learned that if I have something like int.add, right, which is a function of 2 arguments, right? And I know very well that 3.add also exists, right? But let's forget that this one exists at all, right? Let's assume that this one doesn't exist. All we have is int.add, which is a function of 2 arguments, and I want to apply it to the argument 3, right? So in essence, I would like to have the equivalent of x int add of 3 and x, right? That's what I would like to add to have, but not using lambdas. So far this is possible. We already have the elements. We can say Cari of this and apply it to 3, and this is not using lambdas, is not using definitions, and it's perfectly in line with what we want to achieve, right? But it has to use Cari. Now there is another way of doing this which doesn't need Cari. This is a predefined, a built-in function that works with multiple arguments, right? So this is not Caried, it works with multiple arguments. So you can say partial and distance and 3, right? So let's say distance when x is 3. We say partial distance 3, right? So this would be equivalent to lambda y distance 3 and y. So it doesn't use Cari anymore, right? And it's a function that takes as many arguments as we want, and we can partially apply as many as we want. So the result, this guy, is a function to which we can further apply, to 4, and then obtain a result, like 5 in this case it's going to be, right? So partial is sort of, we could have done, instead of int.add, we could have used distance here, right? So Cari distance 3, this expression, is perfectly equivalent to this expression. All right, just that partial comes from a different module. Okay, and this will lead to quite a few very interesting ways of writing code that we would naturally write differently. Let's try to multiply 2 tuples element by element. So we're going to, you can see dot product here, and we're going to try slowly to evolve towards that, right? So take 2 tuples, consider them as being 2 vectors, and compute the dot product of those 2. Okay, so the first thing that we want to sort out is how do we multiply two vectors element by element, two tuples element by element, right? So we already know how to do that, right? Because we've done a similar thing with addition, with add. So instead of add, we use mul, and we use star map, which is something that we have learned, right? We apply it to the zip of the two tuples. Previously we used lists, but it doesn't mean that we can't use tuples, right? And what we're going to get is the result 4, 10, 18, right? So 1 gets multiplied by 4, 2 gets multiplied by 5, and 3 gets multiplied by 6. So multiply element by element, right? We could have this kind of expression for it. Okay? Now, if we were to use this, we would use a def, but we want to not use def at all, right? So can we find a definition that doesn't use def or lambdas? Yes, right? So very similar to what we have done previously. Okay, let me see if I can put both on. All right, I'm going to temporarily delete some of the stuff here, so then they can fit inside the screen both, right? So if you look at this, and if you look at this, they are extremely similar. We are using essentially the same pattern, right? This was a function of two arguments. Right, sorry, a function of one argument, a function of two arguments, right? And we carried this one, we applied to this one, and then we would use compose twice. All right, so it's the same pattern, just that this time this zip is a built-in function written in C, and therefore we have to wrap it. We have to use the wrapped version, right? Otherwise everything is approximately the same, right? So if you look here, this is a partial application. So if I take star map and I want only to apply it to int.mul, then these two make up for a partial application. So this is what we have here, right? So I have partial star map applied to int.mul, and then we have to have the same pattern: compose, compose, compose. Okay, so if you have figured out how this works, you should also be able to figure out how this works as well. Okay, so this is a cool thing. We have managed to define a relatively complex function, multiplication of element by element, without using lambda or def at all, right? Our primitives are compose, all right? Well, we're using partial here, but remember, partial is actually carry applied partially, right? It's just a carry inside here, and wrapped carry, right? So we're using carry or wrapped carry depending on whether the function is built-in or not, right? But this is just a Python specific thing. So we can take this expression, right, and it will multiply all the values element by element. Okay, now you're gonna ask me, well, is this better than this? And the answer is not in Python, but what I'm trying to teach you something is what I'm trying to teach you here is something that transcends Python, right? It's certain principles and certain relationships between lambdas that you can take into learning new languages later, should you want to. By the way, those of you who have learned OCaml will, if you try to replace to translate this into OCaml, where you won't need a wrapped carry, by the way, right? You will see, and also OCaml happens to be carried by default, right? you will see that this expression is actually a very, very simple one, right? And in OCaml, this kind of expression will be much shorter and much simpler, and in general much easier to understand for OCaml, seasoned OCaml programmers than this one, right? The equivalent of this one. All right, so you can spend some time thinking about it, and hopefully you'll figure out how it works. Try to figure out how to perform the dot product, right? And it's relatively simple, right? Because all we have to do is to take sum and apply it to mul lm by lm, right? To this function that we have defined here. So that will give us the dot product, whose value is 332, right? So you might want to say, oh, well, we could define this function, right? But again, we are in the realm, just for this lecture, we are in the realm where we want to define functions without using def or lambda, okay? So now notice the fact that this is in fact a pattern that we have seen before, right? We have a function of one argument composed with a function of two arguments, and we have the two arguments here, right? So since we know the pattern, we know the solution. This is the solution, right? So here we are defining dot product without the use of def or lambda. Okay? And then once we have performed that definition, we can just apply it to two tuples which we consider to be vectors in this case, right? Let's say we're math people, and for us vectors are tuples. And this will evaluate to 332, sorry for the typo. Okay? And this is a very cool pattern, right? We have managed to define something relatively complex, yet again, dot product, right, without using any def or lambda. Okay? So let's remember that, right? Let's remember. Look at this, right? We define multiplication element by element with this. We are assuming that carrying, partial, and compose are no primitives. These are the primitives of our language, and we cannot use def and lambda. So we have defined multiplication element by element in this way. And then we define the dot product using the same pattern, right? Using the same pattern, again without using def and lambda. So this evaluates to 332. So let's assume now we want to do matrix transposition, and before we start with that, we have to see how we encode matrices, right? Because Python only offers us certain ways of aggregation of data, right? It doesn't really have two-dimensional data structures, but we can create our own hierarchic data structures that mimic a matrix. So you see here we have a tuple of tuples, right? We have a tuple of three tuples, each of the tuples having three elements, and you could think of this as a matrix, right? The first tuple is the first line, the second tuple is the second line, and the third tuple is the third line of the matrix. Obviously, we make the underlying assumption that for all these encodings, we will always have inner tuples of the same length, which may or may not be true. And depending on how seasoned we are as programmers, we might be able to actually figure out ways to ensure that this always happens. So now, how do we transpose the matrix? Well, there's a very simple expression that does that, right? So if you think very carefully of how star works, we have a star here, notice, right? Zip star m will transpose the matrix. It's that simple, okay? But what I would like is to have a function that transposes the matrix, right? I would like to have a function called transpose, which I can apply to M, like here, all right, and I get a transposition. This would be an expression, and it's a cool expression. It's cool to remember and to understand that Python can be very concise because of the way it handles arguments. But what I want is to not be worried about the star myself. All right, is the general principle of coding. Whenever I give to a user a piece of code that he should be using, I shouldn't be giving him a cognitive overload as well, right? So the matrix is encoded as a tuple of tuples, and then I have a function transpose, and I just pass the matrix in, and transposition happens, right? The user should not need to know that, oh, zip star M does it, right? It should be as clear as possible. This is a lot more clear. This is a lot more straightforward for a user who hasn't looked at the code before. It is a lot more straightforward to use. Okay, so we want to somehow put this star inside a function, right? And we can do that with a function which we call variable args. We transform between variable args functions and fixed args functions, right? So vargs takes an f and takes a set of arguments and passes them via a star, right? So this is a single collection of arguments. This is a single argument, but a collection, right? A single argument, but that argument comes in as a collection, list, set, tuple, right? And then f is a function of multiple arguments, and then because of the star, that function gets all its arguments. Okay, so now transpose is vargs of zip. Okay, so notice that now we have a relatively simple expression. Once we have figured out that this how to write this function, right, we can have a very simple expression for transpose. Now you're going to say, oh well, we were in the realm of not using defs or lambdas. In this case we can't. This is a very specific feature of Python, and we cannot write this without a lambda. We have to use the lambda. Okay, so now if we evaluate transpose M, it will evaluate to this as an iterator, right? What we're getting is not the tuples, but we're getting the iterator, all right? Which is a detail. Okay, so we can perform the opposite operation, right? So instead of having the star here, we can have the star here, right? So we take a function, we take a multitude of arguments, and this is a function of a single argument, and we pass inside as a single argument. Okay, so in that case, multiplication element by element can be written somewhat simpler, right? So we can have variadic. Well, it's just an alternative way, not necessarily simpler, but it's just an alternative way. So we can have variadic of compose partial star map, right? And multiplication, and then a vargs version of zip, right? So you see how we make it into a vargs and then we make it back variadic. And we can apply the same pattern. These two functions are very similar, right? And we used the same pattern previously in solving both. So we're going to apply the same pattern again, right? So instead of this, we can use sum, all right? And instead of multiplication, we can use the partial application of star map and mul, and then again we have a vargs of zip. So all we need to do is add an extra composition with sum right here. Okay, so these functions are extremely useful, and we're probably going to use them again in subsequent lectures. And obviously, I'm going to reintroduce them at a time, since this part of the course is optional. But these are very useful functions. The next thing that we need to talk about is the Cartesian product, which is a primitive that computes exactly what you expect, right? We have learned about Cartesian products early in mathematics. We take two sets, and then we pair up all the combinations. We create all the combinations of pairs where the first element is from the first set and the second element is from the second set, right? So if we have these two sets of these two tuples, right, we're going to create all the possible pairs: one with 4, one with 5, one with 6, 2 with 4, 2 with 5, 2 with 6, 3 with 4, 3 with 5, 3 with 6, right? And you see all of them here. They're all here, right? We have all the combinations. And this procedure is built in, comes from this module, which is a standard module of Python. All right. And it can work on as many collections as we want, right? So if you say, let's say we take 3 collections, I'm going to make the collections shorter now, because there's an exponential explosion of the result, and I don't want to have to scroll too much. Right? We're going to get all the possible triples, right? Where the first element in the triple comes from the first set, the second element in the triple comes from the second set, and the third element in the triple comes from the third set. All right, and these are all of them. So we should have 2 to the power of 3 here, which is 8. All right, you can count them. It's 8. Here we should have 3 to the power of 2, so we have 9 elements. All right, this is straightforward, right? It's a procedure that would be very easy to write if we didn't have it, right? But I'm not going to waste time to do that. You can try that as an exercise, and then all right, let's do something useful with it. Let's see whether we would find something useful to do. And what I'm suggesting is that we should try all the triples summing up to n first. All right, triples summing up to n. And we can do that by filtering, right? So we can generate all right, so let's look at the naive solution. Sorry, let's look at the naive solution. I am going to return a tuple, right? So notice that this is the start bracket. Let me try to make this a little bit clearer. So 4, 4, 4. So this is a naive solution not using product. And then we have an if, and then this bracket closes there. All right, so this is the main bracket that closes, and this would be the expression, right? So if we were to just generate triples summing up to n, we could use this program, right? We take I in range from 1 to n, j in range from 1 to n, k in range from 1 to n, and we keep only those, right, such that I less than equal to j less than equal to k. So let's say we add that, because we're not interested in repeats. So for instance, if we look here, 1, 3, 5, the sum of 1, 3, 5, and the sum of because we're repeating, right? the sum of 135 and the sum of 351 would be the same, right? So if I were using the same triples everywhere here, the same tuples everywhere here, I would have both the triple 135 and the triple 153, right, or 351, and then all of them go to the same sum, and they're not that interesting, right? Because it's the same combination of numbers. So what we want in order to reduce the number of solutions, essentially, is we just keep the solutions where I is less than j, which is in turn less than k, right? And we keep only those where I plus j plus k is equal to n. And this will give me all the triples whose sum is n. Now, this is triples, right? What if I don't want triples, but I want arbitrary tuples? And by the way, when I say triples here, this is wrong. I should say tuples. And I want to say I want all the tuples of size k that sum up to n. All right? So this is a lot more difficult suddenly, right? Because here, the fact that I had triples means that I have 3 4s. But how can I have a variable number of 4s? If my k is 5, how do I have programmatically 5 4s? Right? When I say 4 is not number 4, but is the keyword 4 here, right? So how can I have 5 4s or 6 4s, or how can I alternate between these 4s depending on an argument k here, right? Not that easy. So we actually have a much simpler solution, because we can use product, all right? And we can create with product arbitrary tuples, right? Arbitrary tuples from any number of ranges we want. Okay, so we're going to take this tuple, all right, and multiply it by k. All right, and let's see what happens when we do that. So let's say I take the tuple of 10 and I'll multiply it by 5. Okay? So remember, instead of 5 I have k, so k is a variable number, right? So I can produce tuples of arbitrary size. And now I can produce tuples of tuples. So let's look at this expression, right? We're producing map range. Map range. So let's do that with explicit numbers, right? So if I say, and I'm going to use much smaller numbers because I don't want to have to scroll too much. So if I'm going to have 3, right, times 3. So this is going to produce a tuple, and I'm going to have map right. So I'm going to have a map. So whenever we do that, unfortunately, map returns an iterator. So to see the content, we should always convert this into a tuple, let's say, in this case, because we want to work with tuples, right? So we have 3 ranges. So now, if I'm going to apply this, to use product on this, what do you think we get? Right, so I'm going to have product, and I'm going to have a star here. Okay, so from where was it from? From itertools. Right, so notice the fact that we can produce all triples of size 3. If I want all triples of size 4, all I have to say is 4 here, and I get tuples of size 4. Okay? Now, why do I need a star here? Well, remember that this is a tuple, but product needs 3 arguments. So I need to convert from a tuple of 3 elements into 3 arguments for product. Therefore, we need to use this star. All right? So to make it even more obvious, I'm going to say that this is T, even though this is not a T, it's an iterator that could be converted into a tuple, but let's say that this is a tuple. And then I will say now product of, I can't say T here, right? If I say T, I get something wrong. I mean, it works, but it's a product of a single tuple whose elements are other tuples. But I don't want a single tuple. I want the tuple converted into argument. So I'm going to have a star here. Okay. So let's see the difference. So if I say product, and let's say tuple here, right? I get a correct result actually. Right? This is actually the correct result. And if I put a star here, right, the tuple gets converted into multiple arguments. Oops. What did I do wrong? Map range. Sorry about the hiccup. So it so happens that iterators are objects that can be only consumed once. So when I used T, I created T here. And then I consumed it once here. And then when I tried to consume it again here, there was nothing to consume, so the result was empty. So actually, let's create the T as a tuple. So let's make T equals, because a tuple, it is an iterator, but it is an infinitely consumable iterator. All right, so if now I say product T, right, and actually I can say tuple right, I get a even though it's a product, I get a product with a single element, whose inner elements are ranges, right? What I want is this. Okay, that's why the star is necessary. So yeah, try to think a little bit about it and understand it. So going back to this again, right? So we're here. So we are producing we are producing all the possible tuples of size k with numbers between 1 and n. All right, and now we have to filter out of this. We're going to filter them, right? So we're going to say, I'm going to, from out of the t's, the tuples that come from here, I'm going to take only those whose sum is n. All right? Only those whose sum is n. All right? And I filtered everything that I need. But now, remember that we wanted everything to be in increasing order, right? We wanted them to be I less than j less than k, right? Now I have tuples of arbitrary size. So how am I going to put them in increasing order? We just use this sorted, right? That will put them in increasing order. This sorted will create an iterator. So again, we convert that into a tuple. And then guess what? We're putting this into a set. Because they are already sorted, the tuple 351 has become 153. So now 135, sorry, because they have to be increasing order, right? So 135 will appear several times, right? Because 135 is there, 153 is there, 351 is there, 531 is there. All of them, when sorted, are going to become 135. And then we want only one instance of them, right? So to ensure uniqueness, we use a set. All right? And then to make the output elegant, we also sort that set. And we produce a tuple of results. Okay? So using product, we have the advantage that we can produce tuples of arbitrary size. This is a very interesting problem, right? So think of that, right? Look at the output, because that will probably make it more compelling. So I want all the tuples, not triples, tuples, summing up to 10 and of size 4, right? And these are all of them. Right? This is not something that is easy to generate off the bat, right? So the length, the size of the tuple is unknown beforehand, right? We decided to be 4, and we have now all the combinations of digits between of four numbers between 1 and 10, or 0 and 10, which when added together, 0 and 10 essentially, which when added together produce 4 of them produce the sum 10. Okay, so this is a kind of a non-trivial problem, and it is made very simple by the primitive product. The last thing that we want to learn in this optional lecture is the reduce operation. All right, it is defined in several packages. I think GitterTools might have one as well. And it is a function that gets applied, takes a binary operator and places that binary operator between all the elements of a list, left biased, right? So, for instance, this is the equivalent of sum. And what happens here, right? What happens how does reduce evaluate everything? Well, it will compute, I'm going to just say a instead of add, int.add. So let's say that a is int.add, so I can save some typing, and it's going to compute a of 1, 2, and 3, right? So it's going to perform this kind of operation between all the elements of a list. If I would add a 4 here, right, then we have to add an a at the top and then a 4 here, right? So this is what gets computed. Now imagine that this A is actually an arbitrary function of 2 arguments, and it will perform this operation between any 2 arguments. So for instance, if we have a minimum function, one that works between 2 numbers, min, right, then you can use it to define a min that works for lists or collections. All right. So this would be such a function. This would be a min working between 2 numbers. And then by using reduce, right, this will start working as a min, as a minimum function over a list. All right, so it can be used to define min over functions. If I didn't have sum, if sum wasn't a built-in, then we could just define it in this way. Right, so now that we have reduce and we know that we have addition, we can just partially apply reduce to addition. We get a summing function. So this completes our excursion into higher order programming, right? This is what we have learned. How to learn with functions whose arguments are other functions. This is what higher order programming means. This is about it. There is a lot more, all right, but given how short this module is, I won't bore you with the rest of the details. Should you want to learn more, feel free to approach me and I can point you in the right direction. Thanks for watching this. See you in class.